Welcome to today's lesson. Today we will be discussing Einstein's theory of relativity and also related concepts like time dilation, length contraction, and the change of mass with motion of an object. By the end of 19th century, scientists thought that theoretical physics has almost come to an end because with Newton's laws of motion and the idea of gravitation, and also along with that Maxwell's theories on electricity and magnetism and the kinetic theory of gases, they thought the whole of the physical phenomena which are observed in this universe could be explained by the physics which were existing at that time. But in the beginning of the 20th century, a young physicist, only 26 years of age, Albert Einstein, showed us how space and time changes with the observer when he is moving with relation to what is being observed. To say that Einstein's theory of relativity revolutionized physics will not be an exaggeration, because this relativity connects space and time, matter and energy, electricity and magnetism. And these links are really crucial to our understanding of this physical world. Following this relativity, there came a host of predictions, all of which have been confirmed through experiments now. The best part of it is that they all can be derived with simplest mathematics. So today we will be learning Einstein's theory of relativity. Einstein put forward two theories of relativity: special theory of relativity in 1905 and general theory of relativity in 1960. A decade later. But special theory of relativity have more implications on the motion of objects. So today we will be focusing on special theory of relativity. In simple words, we can say that it states all motion is relative, and the speed of light in free space is the same for all observers. We will discuss that further as we proceed with the lesson. And general theory of relativity describes the relationship with gravity and the geometrical structure of space and time. We will not be focusing on the general theory of relativity now. Now, before going to special theory of relativity, we have to clarify the concepts on frames of reference. When do we say that a body is in motion? We say that a body is in motion if its position changes with time. So when a body's position changes with time, we always refer to its position with respect to a coordinate system. We usually use the Cartesian coordinated system, which is fixed on Earth or in a laboratory where we are doing the experiment. So frames of reference are a specified coordinate system in three-dimensional space with respect to which the motion of an object is described. Now, these frames of reference can be of two types: inertial frame of reference or non-inertial frames of reference. Now, inertial frame of reference is any system moving with a constant speed with respect to each other. And in such frames of reference, Newton's laws can be achieved. In this frame, a free body does not exhibit acceleration. Or you can tell in simple words, all non-accelerated frames of reference are called inertial frames of reference. Let us consider we standing on ground and a train going at a constant velocity. Then we can call ourselves and the train are in inertial frames of reference because the train is moving with a constant velocity with respect to us. So the two frames of reference or two systems under consideration should have a constant relative motion, or they can be at rest. Then we call them inertial frames of reference. On other way, non-inertial frames of reference are frames which have acceleration. For example, if we are standing on ground and there is a merry-go-round going near to us, circular motion, as you all know, are accelerated motions. So we cannot call ourselves and the merry-go-round as inertial frames of reference. They are non-inertial frames of reference, which means accelerated frames of reference. So inertial frames of reference will be either at rest or they will be moving with constant velocity with respect to each other, while non-inertial frames of reference are accelerated frames of reference. And Einstein's special theory of relativity is applicable for inertial frames of reference only, not to non-inertial frames of reference. Now let us see the postulates of special theory of relativity. There are two postulates for special theory of relativity. The first postulate states that the laws of physics are expressed in the same form in all inertial frames of reference. What does that mean? For example, in one frame of reference, if we consider F is equal to ma, force is equal to mass times acceleration, and if we consider an event which is taking place in an inertial frame of reference, that is another frame which is moving with a constant velocity with respect to us, and there also the same laws of physics are valid. There also we can apply F is equal to mass times acceleration. But if the other frame of reference is non-inertial, which means if it is accelerated, we cannot consider the laws of physics in the same form. It will change. In all accelerated frames of reference or non-inertial frames of reference, there will be some fictitious force acting. We remember in circular motion, there is a centripetal force. That is a kind of fictitious force which is acting in accelerated frames of reference or non-inertial frames of reference. That is the first postulate put forward by Einstein in 1905. Now the second postulate states that the speed of light in free space has the same value in all inertial frames of reference, and the value usually we express as 3 times 10 raised to 8 meter per second. To 4 significant figures, we can tell it as 2.998 times 10 raised to 8 meter per second. Now the speed of light in free space have the same value. To make it more clear, let us consider a hypothetical experiment which is shown here. See, here in figure A, what you can see is a searchlight. It gives out a pulse of light. And if we are standing on ground and measuring the speed of light, which is traveling in air, which we can consider same as that in free space, we will measure its speed as 3 times 10 raised to 8 meter per second. Suppose when we are giving out this pulse of light, at the same time, we are allowing a spaceship to travel with a velocity 2 times 10 raised to 8 meter per second velocity. Then, by our common sense and also according to the relative velocity concept put forward by classical physics, we expect a person traveling in the spaceship to observe the light traveling at a velocity 1 times 10 raised to 8 meter per second. Why? Because both the light and the spaceship are traveling in the same direction. So according to classical concept, the velocity, the relative velocity of this light pulse will be 3 minus 2, which is 1 times 10 raised to 8 meter per second. But According to special theory of relativity, the speed of light in free space has the same value in all inertial frames of reference. So, according to special theory of relativity, a person who is measuring the speed of light in the spacecraft will also measure it as 3 times 10 raised to 8 meter per second. So its value is constant, whether there is a relative motion between the observed light pulse and also the person who is observing that. So irrespective of the frame of reference from which it is observed, irrespective of the motion of the frame of reference, speed of light have the same value. I will tell one more example. For example, we have 2 light pulses. We know that now light is made of photons. Suppose we have 2 photons, A and B. They are identical. Now, if photon A is moving towards east and photon B is moving towards west, then what will be its relative velocity? Common sense and classical physics tells us that they are moving in opposite directions. So one photon will observe the other photon as moving very fast, as we do so while traveling in 2 cars which are traveling in opposite direction. So we have a tendency to say that their relative velocity will be 2 times 3 into 10 raised to 8, which is 6 times 10 raised to 8 meter per second. No. According to special theory of relativity, their relative velocity should be 3 into 10 raised to 8 meter per second itself. So that is the speciality of special theory of relativity. It is beyond our common sense concept of finding relative velocities when it is for light in free space. And there is one more thing which I would like to discuss at this point. The speed of light in free space is the ultimate or the maximum velocity any object can have in the universe. Nothing can have a speed greater than 3 times 10 raised to 8 meter per second. We know that light has its maximum velocity when it is traveling in free space. But when light is traveling in any media, then its velocity will be reduced. For example, if light is traveling in matter, its velocity is reduced. It will be less than 3 times 10 raised to 8 meter per second. But there are some elementary particles which can travel to a speed nearer to the speed of light, but less than that in free space, and when they travel in a material, their speed will be more than that it will travel in free space. So inside a material, if we take, then the speed of light will be less than 3 times 10 raised to 8 meter per second, and elementary particle may have a speed comparable to that of light, but less than 3 times 10 raised to 8 meter per second, but it can have a speed which is slightly more than the speed of light within that material. That may occur, but even within the material, no elementary particle can travel with a speed which is more than 3 times 10 raised to 8 meter per second. So that is the ultimate speed limit any body can have under any circumstances. So let us proceed to discuss different concepts which came as a consequence of this special theory of relativity. The first concept is time dilation. What does that mean? A moving clock ticks more slowly than a clock at rest. What does that mean? When a body is moving at very high speed, a speed comparable to that of light, then when we observe the motion of that body, then we feel that the clock inside that ticks more slowly. That is, the time is dilated. The time interval is increased. So if we are standing on ground and observing 2 events, the time interval between that two events are measured as, suppose, T0. T0 is the time interval on a clock at rest relative to the observer, which is also called the proper time. So if we are looking at the events which are taking place on ground, when we are observing them on ground, and we measure their time as T0. Now, if the same events are occurring in a spaceship which is traveling at a speed comparable to that of light, let us say the time of the time interval between the events which are taking place inside the spaceship as T. That is the time interval on clock in motion relative to an observer. Then the time which is observed in the moving frame is equal to T0 divided by root of 1 minus v square by c square, where v is the speed of relative motion and c is the speed of light. So here you can see that here this quantity will be less than 1. So if any number is divided by a number less than 1, you will get a greater value. So the time take as measured by the person standing on ground for two events which are taking place inside a spaceship which is traveling with a speed comparable to that of light, then we see that the time interval is more than for the same events which are taking place on ground. So the time interval between the occurrence of two events which are in motion with respect to the observer will be longer than the time interval of occurrence of the same two events which are at rest with respect to the observer. Now you will get more clarity with numbers when we solve numerical problems related to time dilation in this lesson. And I will also derive this expression taking into consideration Lorentz transformation equation, which will come in the next lesson. Okay, let us illustrate this time dilation with a hypothetical example. Suppose you have a clock which consists of two mirrors, and in between these two mirrors there is a light pulse. When the light pulse is emitted by this plate, it goes up, and here it gets reflected back and it comes down. So let T0 be the time taken for one round trip, and this is observed from ground. So T0 will be equal to 2 times L0. L0 is the distance between these two mirrors, and c is the speed of light in free space or in air. So the total distance traveled when it makes a round trip is L0 plus L0, which is 2L0 divided by the speed. So time T0 is equal to distance by speed. Now let us consider the same clock as moving with a velocity v, which is large, which is comparable to that of light but less than light's velocity, and it is traveling in this direction. Note here that this is the direction in which it is traveling, which is normal or perpendicular to L0. So L0 is not changing. The mirror or the clock is traveling in this direction with a velocity v. So by the time the light pulse reached the upper mirror, the mirror must have moved a distance v times t by 2. If t is the total time taken to make this round trip. So by the time the light pulse reached this mirror, upper mirror, it must have moved a distance v times t by 2, because the whole device is moving with a velocity v. Now light is traveling with a velocity c. So the light travels here a larger distance. See, it doesn't travel this distance L0, it will travel a distance given by speed times time, that is c times t by 2. So we can consider this as a right triangle with the hypotenuse c times t by 2, base v times t by 2, and height L0. So using Pythagoras theorem to this right triangle, you can get ct by 2 the whole square is equal to L naught square plus Vt by 2 the whole square. Hypotenuse square is equal to height square plus base square. So here rearranging the equation, taking this term to the other side and taking t by 2 the whole square as common, which is t square by 4, you will get c square minus v square is L naught square. So again, our intention is to find an expression for t. So keeping t square on one side, taking 4 and c square minus v square to the other side, you will get this expression. Taking c square outside, it will become this. And we know that E naught is 2 L naught by c. So I'm substituting here for 2 L naught by c t naught. So here we have taken the square root and we got this expression, and instead of t naught or 2 L naught by c, I'm substituting t naught, and we get this expression that t is equal to t naught by root of 1 minus v square by c square. That is, when you stand on ground and measure the time interval for the complete round trip of this light pulse to go up and come down, you will find a new time t which is larger, which is dilated time compared to the proper time t naught. Okay, now let us go to another interesting concept, which is also a consequence of Einstein's special theory of relativity, which is called length contraction. What is meant by contraction? Contraction means reduction. So length reduces when a body moves at a speed which is comparable to that of light. Means faster means shorter. So the length of an object in motion with respect to an observer appears to be shorter than when it is addressed with respect to him. So length of the object in motion with respect to an observer appears to be shorter than when it is addressed with respect to him. Or we may say that if L naught is the length of the object when it is addressed with respect to the observer, which is called the proper length. And then if L is the length of the object when it is in motion with respect to the observer, V the relative velocity with respect to the observer, and C as the speed of light, then the new length, that is the length observed, will be L naught times root of 1 minus v square by c square. You know that this is less than 1. So when you multiply a number which is less than 1 to a number, you will get a lesser number. Okay, so let us see what is meant by length contraction. So if you are standing on ground and if there is a spaceship which is moving at very high speed comparable to that of light, then when you observe it from ground, you feel that its length have reduced. You feel that the apparent length of the rocket measured from ground will be less than when you measure it when it is at rest on ground. And here you have to note this contraction of length occurs only in the direction of motion. Any other dimensions which are normal or perpendicular to the direction of motion will not be affected. We will see more of it when we solve numerical problems related to length contraction. Okay, now let us consider the next concept, increase of mass, which means the mass of a body is not the same as when it is at rest. If a body is moving with a speed comparable to that of light, the mass of the body increases. And it increases with the speed of the body. More fast the body is moving, more will be its mass. So if we consider m naught as the rest mass of the body, m as the mass of the body while it is in motion, and then we can see that the mass of the body while it is in motion is m naught divided by root of 1 minus v square by c square. Here again we know that 1 minus v square by c square is less than 1. If you divide m naught by that number which is less than 1, you will get a greater quantity. So here again we see that when a body is moving at a very high speed, it appears that its mass is increasing. Okay, we know Newton's equation that converts mass into energy, Einstein's mass energy relation, and here E is equal to mc squared. Now if the body is at rest, we can say that here we will use m naught, the rest mass of the body. Now if it is in motion, we may expect, if we are converting that mass into energy, a larger amount of energy will be released. We never know whether it is true or not. Now, one of the most important outcomes of Einstein's special theory of relativity is the mass energy formula itself. And it states that mass is a form of energy, and it's the source of power for many of the radioactive materials, and it is the basis for nuclear power station. Even sun, which acts as the source of energy, and it is running out of, it's not running out of fuel for millions of years, and the source of energy from sun is also nuclear reactions, and this is the energy equation which is followed there while mass is converted to energy. Now let us consider some numerical problems related to time dilation, length contraction, and increase in mass, which will make those concepts more clear to you. So let us consider the first question. An astronaut at the age of 30 years went to investigate the Milky Way by a spaceship moving with a speed of 2.4 into 10 raised to 8 meters per second and returned after 50 years. According to the calendar of Earth, what will be his age? At this stage, you can pause the video and solve this problem by yourself and come right back to check your solution. Okay, let us check the solution. See, this is the solution. So here, the astronaut started off at 30 years of age and he's traveling with this speed. So he returned after 50 years. So this is the time measured from ground for a body which is traveling with a high speed. So t is equal to 50 years and velocity is given, speed of light, you know, and you have to find what will be his age. So let us see on ground, if he has a twin brother, how much time will be passed? So you can see t is equal to t naught by 1 minus v square by c square. Rearranging this equation because we have to find t naught, you will get it as I have substitute here, oh, it should be 50. I'm sorry, I wrote it 5, but I calculated using 50. It 50 times 1 minus 2.4 into 10 raised to 8 divided by 3 into 10 raised to 8, the whole square. It should be 50. I calculated it right, but here while writing I missed that 0. So this is equal to 30 years. So the age of the astronaut will be 60 years when he comes back after 50 years. Now here comes an interesting concept which is called the twin paradox. Suppose the astronaut had a twin sister. So they started off for the journey at 2100. And when he comes back on ground, in the calendar on Earth, it is 2150. So 2150. While in his clock, which is dilated, it is 2130. So what we expect him to have is just 60 years of age, while his twin sister who was staying back on Earth have passed 30 years plus 50 years. So she will be 80 years of old. So what is the paradox here? The paradox is that whether this twin sister will look 80 years old, or whether she will be more wiser than his twin brother because she have completed more years, and whether she will be looking so old and her physiological developments must be taking place at a faster pace than him. We never know. We have never conducted such an experiment because all the spaceship which we have developed so far have its velocity a few times 10 raised to 4 meters per second. While to have a significant difference in this time dilation, there should be a speed which is around 2.4 into 10 raised to 8 meters per second, which is comparable to light. We never have made a spaceship which can travel with high velocity, and also we never sent spaceship for this many years with a human being inside that. So we haven't conducted this experiment, so we never know whether they will the age difference will be there when he comes back. And there are other concepts to consider, because when he is traveling, when he observes the person on ground, he feels that their time is delayed because it is v squared. So if it is v or minus v, when we take v squared, the effect is same. So he will be feeling that there, for her twin sister, the time is dilated. And also when he is traveling with this speed, he will be traveling to a place which is around 25 light years away. And then when he is traveling, he will feel length contraction. He will not feel that much distance which he has to travel. So all these factors have to be taken into consideration. So it still remains a paradox. Now let us go to the next problem. All the experiments which are related to time dilation are conducted in elementary particles which can travel at a speed comparable to that of light, and this time dilation also is experimentally confirmed. Now let us look into the second question. A spacecraft is moving relative to Earth. An observer on the Earth finds that between 1 p.m. and 2 p.m., according to her clock, 3,601 seconds elapse on the spacecraft's clock. What is the spacecraft relative speed on Earth? So now you pause this video, try to solve, and come right back to check the solution. Let us see the solution here. So here they have given this time which is calculated or which is observed by an observer who is on ground. So the moving body time elapsed is 3,601 seconds. Since this is given in seconds, we know the time difference between 1 p.m. and 2 p.m. is 1 hour, which is expressed in seconds, 60 times 60, and you will get this value. And now we can use this formula, and substituting all these values, rearranging the equation, you will get V as equal to 7.1 into 10 raised to 8 meter per second. This is more or less a straightforward problem. So let us move to the next numerical problem. So the length of the rocket is 100 meters on the Earth. When it is flying a person on Earth, its length is measured as 900 meters. What was the speed of the rocket? This is also a straightforward question similar to question number 2. So pause the video here, solve it, and come right back. Let us check the solution. So this is again, they have given the proper length and also length of the spacecraft when it is measured while traveling, and you have to find its velocity. So It's direct substitution in this equation and rearranging, find the value of V. So check your solution here. And if it is right, go right to the next question. Okay. So in a physical laboratory, Hudson found the density of 1 meter long metallic object as 19.3 into 10 cube kilogram per meter cube. On the other hand, Ahmed determined the density of the object in a spacecraft moving with a velocity 0.9 c along the length of the object. Along the length of the object. Find the length of the object in the moving frame, which is straightforward. You just have to use the formula for length contraction. Will Hassan and Ahmed get the density of the object same? Well, this is a bit twisted. Note here that density of an object is mass by volume. So mass will also change when the body is moving with such a high velocity. So you will have to use the relation m is equal to m naught by root of 1 minus v square by c square. Again, while you are considering, there is volume. Volume means length times the area which is perpendicular or normal to the direction of motion. So you can consider the length contraction only for the length, while for area there will be no change. It won't be affected by the motion. So pause this video, solve the problem, and come right back to check the solution. So here is the solution for A part, which is very straightforward, direct substitution of values, and here comes the B part. So they have given the density when the body was at rest. You have to find the new density. So density, which is expressed by the symbol rho, is equal to mass by volume. Volume, you know, is area times length, the normal area times length. Then mass is equal to rho times area into L. And we know this proper length and also the contracted length here while moving. So you know L naught and L. So I'm taking into consideration the relative equation for mass and substituting for m rho a L, and for m naught rho naught, which must have changed, L naught, which must have changed, and A with no change. So when I take the density of the object while it is moving, and by rearranging the equation, you know that area gets cancelled, and you know the value of rho naught, L naught, L. Substituting all these values here, rho naught is this one, and L naught is given in the question as 1, and L we found out in the A part, and V is also given, C you know, and C square gets cancelled here, and solving this numbers, you will get this expression, this value. Check your solution and go to the next problem. So the next question, the last question, is the length and mass of a rocket on Earth are 10 meter and 5,000 kilogram respectively. It started moving with a velocity 3 times 10 raised to 7 meter per second, which is also comparable to that of light with respect to a stationary observer on Earth. Find the length of the rocket while moving. Like the previous question, this is A part is straightforward, and B, if the velocity of the rocket is doubled. So you have to take, in second case, double of this velocity. What change in mass will take place? So first you have to use the relative mass equation. Find the mass of the object with this as the proper or rest mass, this velocity, and also you have to find the relative mass with double this velocity and find the difference between them. Pause the video, solve the question, and come right back to check the solution. Okay, let's see the solution. So this is the solution for A part, which is straightforward. And this is the solution for B part. So we took the rest mass as 5,000 kilogram, took velocity v1, the first case when velocity is 3 times 10 raised to 7 meter per second. We used the relative mass equation and just substitution and solving, you got this mass. Now second time, as a second case, we are taking twice this velocity, which is 6 times 10 raised to 7 meter per second, and we found the mass using relativity equation, and we got this value. See, this value is definitely bigger than this one. So as the speed increases, speed becomes double, the mass increases. And the change in mass is 77.915 kilogram, which is significant. So that's all. We have come to the end of this lesson. If you have any doubt, you can ask the doubt in the comments below. And if you need other videos which will be related to modern physics as well, you can subscribe to my channel. And if you like this video, please like it. And if you have any doubts or suggestions, you can give that in the comment below. And also here in the description, I have given the link for a video that discusses Michelson-Morley experiment, which set the stage for Newton's special theory of relativity. So bye-bye, keep safe, keep your interest in physics, keep studying. Thank you for watching.